Josh Kosky, and today we're going to be doing the coding interview. So let's take a look at the problem. Okay, the sequences are not necessarily of equal length. It's a little confusing because it says of equal length. More than one combination of occlusions and matches may result in the same answer. So we want an m by n runtime, where n is the length of the DNA sequence and m is the length of the other. Okay, and we want m by n space. So I think to do this, what we're going to do is use a dynamic programming problem. So first what I'm going to do is take your method signature that you guys gave us. So let's copy this over. And today I'm going to be working in Python. So copy that over. So we have a DNA match. So first what we're going to want to do is go through the length of the DNA 1 and the DNA 2. So to do this, and this will keep the m by n runtime we want to do for I and j, or for I in range. First let's get the length of DNA 1. And then we'll say DNA 2 length. So what this is doing is taking the length for the DNA 1 sequence and the DNA 2 sequence and basically giving us what those values are. Okay, so what we're also going to want to do is to create our m by n matrix, which will basically serve as our space. This is our m by n space. So what we're going to want to have to do is do np or DNA cost. We'll call it DNA cost because it's going to hold our cost equals np.zeros, and then we're going to make it m by n. We want to do DNA 1 length and then DNA 2 length. Okay, so this will initialize a m by n matrix, all with zeros in it. Okay, so now to get to our m by n matrix, what we wanted to do is go 0 through DNA 1 length, and for j in range 0. So this creates an m by n matrix, which will basically iterate through every single one of our lists. Okay, so let's go back for a second and take a look at the problem. So now that we have our m by n, we're iterating through with m by n runtime, and this is going to store it in an m by n matrix. So this is space of m by n. We basically want to now process the problem. Okay, so it seems like there's going to be 3 separate cases. One is going to be when it's matching, another is going to be when it occludes, and then a third is going to be when it occludes in the other way, or the other list, since both lists have different occlusion costs. So what we first want to do is say, let's say occlude 1. Okay, so this is going to be the first occlude. Okay, and what we want to do is basically say, what we want to do is, for one sec, first we want to make sure that both lists aren't empty. So what I'm going to do, because otherwise this would be poor for the indexing of it, so I want to make sure that I does not equal 0 and j does not equal 0. Okay, and if this is true, I'm going to handle my base case. Otherwise, I'm basically going to return DNA cost of I and j equal to I times occlusion 1. And this will basically say how many times it's been occluded to that position. So now that we've taken care of this edge case, basically, which is when they're empty, or we just have to occlude to the end of the list, I want to take care of my base case, or not my base case, but basically our general cases. So for this, we want to do, I basically want to get my DNA 1 sequence and my DNA 2 sequence for my occlusion costs. So basically, we're going to call this one occlusion 1. And we're going to call this occlusion 1. So what we're basically doing, and I'll explain this in a minute, is taking the DNA cost weight that is previously being recorded in the index before it. So what it's going to be is I minus 1 and then j. So this basically stores the occlusion cost for what it was in that value to occlude at that point. Okay, so now we're going to make an occlusion 2, which also stores occlusion 2 plus DNA cost of I and then j minus 1. And what this does is it stores in the other part of the indice before it in the diagonal pattern. It's going to basically store the value there. And then what we're going to have to do is also create, so these are for the two occlusion cases, but then this does not account for, and this will account for different size lists too because of our for loops and the iterations of it. But we don't have accounted for is the base case where we match at that indice. So to do that, I'm going to create a helper function. So let's call it define match, and it takes in two things, char1 and char2. Okay, and then so what I'm going to do is return the absolute value. And to do this, oh, I forgot to do this earlier. So I'm going to have to import numpy as np. And what that will do is basically it just imports a standard library, which has a lot of different mathematical functions and other matrix dealing functions and stuff like that. So I'm going to take the absolute value of the difference between these two, but I need to take the ASCII value of it. So it's going to be something like the ord of char1 and char2. Okay, so what this is going to do is basically handle it for that case to see what it is. So now I have the occlusion cost at that given position, and I have the occlusion cost of that given position before it. So now I want to get it at the match position. So what I'm basically going to do is say matched equals, and then we want to do match of DNA1 or excuse me. And what I'm basically doing is I'm taking the current position of that index. And then I'm going to say, excuse me, sorry. And then I'm going to match it with the one in the second position as well. So what this is going to do is basically iterate through and just compare each thing in the list and check to see what that value is. But what we also want to do is add the previous cost to it, because that's like this part will only get it at that current value, but will never consider the previous weights for it. Therefore, it will never update the value. So to update the value, what I want to do is basically just say DNA cost of I minus 1 and j minus 1, and that will basically give it the cost before it as well as the updated match cost. Okay, so this was basically our three updated values, but now what I want to see is which is the best value, because this is what we want to decide before moving to our next piece, or our next part of the letter, I guess, because it processes each thing letter by letter and basically at the same time. I'll explain this in a little bit, but when I do the walkthrough of the case, but just give me 1 minute here and bear with me. So now what we want to do is basically take the lowest cost of the three. So to do this, I'm basically just going to do an NP minimum of two things just to save space. So I'm going to do match or occlusion 1 and occlusion 2. And then I'm also going to do it with matched. So this will take the lowest of the three values, if that makes sense, and basically put it in lowest cost. And then from there, what I want to do is, now that I have the lowest cost of the three, it's basically going to tell me which move is the lowest at that given position, and then it's going to make that move accordingly and store that weight in the current indice index. Okay, so then from there, what I want to do is just basically store in DNA cost to that given position. So basically what I've been doing for all these I minus 1s and j minus 1s is basically I'm storing in the previous indice positions in that matrix what its previous weight was. And I'm comparing it and adding it with its current move to see which one would give it the best value. So now, once I figured all that out and which one is the minimum, which I do in this lowest cost line here, after that, what I basically want to do is just store it in. Okay? And then after that, I think I've basically taken care of everything. Because this will account for everything. So let's go through it for a second and explain to you what exactly is going on. because I can understand how this can get a little confusing. DNA cost, and then DNA length. Then DNA2 length. Okay. So once I'm returning this, I'm basically returning the bottom right position. Let's say it was a matrix like this. There. This is bad. One, two, it would return right here, this value, because it's the bottom rightmost value, which basically stores the least greatest value, the least greatest cost. So basically, it returns the best cost. Excuse me. Sorry. So now, once I do this, I just kind of want to return, and I think everything should be good. So let's just go ahead and double check that everything's good, first of all, and then we'll run through a couple cases once this is compiling. Okay. Interesting. So this doesn't seem to like NumPy, so I'm just going to take this offline because, yeah, I know NumPy is a real function. So let's just do terminal. Emacs final. Okay, this is a brand new file. And then okay. Let's just do something like that. Okay, so let's just do Python. Okay, so now it does that. Let's see if we can run a match DNA. Uh-oh. Okay, so you guys want, let's go over these cases first, and then I'll go over like two more just to exemplify my point. So what this first case is going to do is basically exemplify that okay, I think it should work. Okay, so let's take a look. So the first one should return 19, as it should, because so we're rolling through and we see A and A, which match the same. So that should equal 0 for the first case. We see A and T, which does not match the same. So therefore, we need to do the ASCII difference between the two, and which returns 19. So then we're going to store 19 in that value right there, or in my current position, and then it's going to move to the next part, which is C. And so C returns 0 as well, but then it looks back upon my previous position and see that A and T have stored 19. So then it's going to record 19 there as well. And that's going to see that for G and G, it also returns 0 for the ASCII value compare. So then when it looks for the occlusion cost, it's not going to occlude at all. It's going to use that best value. But then it looks back previously upon the C and the T, or the C and the C position before in that previous value and see that their minimum value was 19, and therefore it's going to use that as the lowest value. What we also see for this one, as you guys have clearly demonstrated, is this will also return 5 because the matching of the value, which is 19, is a higher value than the occlusion cost of the two. So therefore, what that's going to do is, if we look here, that was bad. Yeah, so if we look here and here, what's going to happen is basically A and A are going to be the same and put 0. T and T are going to be the same and put 0 in that position. A and C are going to be that position. A and C are not going to be at the same position, so it's going to occlude in A. C and C are going to match up, which are going to be 0, and then A and T are going to see each other. But since their occlusion cost is lesser than the two of matching the two up, it's clearly going to be just go with the 2 occlusion and equal 5. And if we see in my results here, it's clearly 5 and 19, as they should correctly be. But I don't want to stop right here to show you the examples. I'd like to go a little bit further. So what I'm going to do, I just do Emacs final389.py. So what I'm going to do is add like 2 more match DNA. So I'm going to show 2 cases when one is not empty at all, or I'm going to show 3 cases actually. So you can, so what I'm going to show is one when one is not the same length as the other. One is when one is bigger than the other, or one is less than the other size, and then the other when both are empty. Both lists are empty, excuse me. So first, let's show this. And I'll also show when okay. So what we're going to do is show here that I'm basically just showing that it works for both lists. So now that we've done that, let's run it. So it should equal 19, 5, 3, 0, and 2. So let's take a look at the 3, 0, and 2. So the 0 should be good because that's when we basically so that's when we do this right here, which basically should be 2 empty lists. Therefore, the occlusion cost should be 0 because we're never going to have to occlude anything. For 3 over here, it should only be 3 because it occludes once on the right side. So that's correct. And then for 2, it should be the same thing because it occludes only once on the left side. Therefore, that should be occlusion cost of 2. This shows that we've accounted for basically everything that is 2 lists of not equal length, as well as the fact that there could be more than one combination of occlusions. We've gone through an n by n runtime by doing just the length of the list and the length of the other list by running through 2 for loops with that. And then we've used m of n space by just using an n by n matrix with np.zeros. So other than that, I've shown that this is a correct algorithm. I've shown the explanation of n by n runtime. I've shown that my algorithm uses n by n space, and I've walked you through, I guess, 4 cases. Yeah, and that's it. Thanks so much.